in this section, we're going to try to put ongoing climate change into context. And we're going to do this by looking at how and why Earth's climate has changed over the past on various timescales, on thousands of years, millions of years, longer. And we'll start by describing how global climate is measured. So now there's actually lots of ways to do this to reconstruct climate, from ice cores, from tree rings, and honestly, going through this could be a semester's worth of content in itself. But here we're going to sort of focus on one of the ways that we can get an integrated temperature of Earth over long time periods, and this is the delta 18O proxy. So in this video, we'll go through how and why the delta 18O proxy works. This is based on the isotopic composition of water that's then recorded in the calcium carbonate shells of plankton and these organisms called foraminifera or forams. We'll walk through how and why this quantity reflects global ocean volume and temperature, and how this changes in a coherent way over things like glacial cycles. So before we start going back in time, let's take a moment to examine our current climate. Now, there's obviously a great diversity in climates throughout our present-day Earth. Different regions vary in terms of their temperature, how warm or cold they are, how much rainfall they get, how much direct sunlight, how much cloudiness. All these sort of impact the environment of any given location. But a really huge influence on climate, sort of in huge parts of the northern hemisphere, is the progressions of seasons. This video shows satellite snow cover from 2010, 2011. You can see that when you have winter, sea ice in the Arctic Ocean expands further south. There's snow that covers Siberia, Canada, lots of mountainous places everywhere else. And then when summer happens, this retreats, but then the opposite thing happens in the Andes. And so what's happening in winter is that for a few months at least, so this may be a bit obvious, but what's happening in winter is that you have all of this water that comes down, lands on the Earth as snow, and it sort of stays there for months at a time. So where is that snow from? Well, the immediate answer is it's from the atmosphere, right? It is in clouds as water vapor, and then that freezes and then falls as snow. But before that, it's mostly evaporated from the ocean. So the ocean is the ultimate source of water that provides snow on the northern hemisphere in winter. And you can imagine that with every foot of snow on land, there's that much less water in the ocean. And so you can imagine sea level falling just a little bit. So now this map is a representation of the Earth 20,000 years ago. This is the last ice age that we mentioned when we were discussing the biological pump. But instead of a foot or two of snowfall, now we have a mile thick of ice that covers parts of Canada and northern Europe, and you have extended glaciers that are permanent throughout the Himalayas, other parts of Asia, and southern Patagonia. So all of this is water that's been evaporated from the ocean, and it's landed on the Earth, and it's stayed there year after year as snow and ice, and this is how the ice sheets build up. But one of the nice things about this map is that you can kind of see the counteracting effect. All of this snow and ice that's built up on land comes with the consequences of falling sea level. During these glacial periods, 20,000 years ago, this is a drop of 100 meters or so. So you can see some cool changes compared to our current map. You can see here there's now a land bridge between Australia and New Guinea. This allows organisms to travel back and forth during these times. You can see Southeast Asia is connected by this giant land bridge as well, versus today you have all these Indonesian islands that are isolated systems. You probably know more prominent examples like how the Bering Strait becomes a land bridge, and this allowed humans to go from Asia into the North American continent and into South America. And there's other examples too. For instance, like England was connected to Europe. The Red Sea was closed off, so it's really more of a enclosed basin. Now it's not connected to the Indian Ocean. So how do we know this? And really the answer comes back to isotopes. If you remember from the start of the semester, we talked about three major isotopes of the element oxygen. There's oxygen 16, oxygen 17, and oxygen 18. Here we're just going to focus on the two most abundant ones, oxygen 16, which is over 99.7% of all oxygen. This one has 8 protons, 8 neutrons. Then you have oxygen 18, 8 protons, 10 neutrons. This is only 0.2% of the oxygen out there. Another way to represent this is 2 per mil. So you know how percent is 1 over 100. Do the same thing with per mil, which is 1 over 1,000. So 0.2% equals 2 per mil. A lot of the times when we're talking about changes in isotope differences, they're really, really tiny. So we tend to prefer this per mil notation because it lets us deal with real numbers and not decimal places and fractions. And so another thing that's very common is to see differences in isotope abundances, differences in the relative amount of oxygen 18 versus oxygen 16, reported in what's called delta notation. So here you see the Greek letter delta and then 18 oxygen. And this is just a simple way to compare different abundances of oxygen 18 versus oxygen 16 in different samples. So the way this works is you have your measured oxygen 18 to 16 ratio in a given sample. Maybe it's seawater, maybe it's calcium carbonate, maybe it's ice on land. You compare that to a standard that everyone uses. And so this is just a good reference point. Then you subtract 1. And then, because that's a really small number, you multiply it by 1,000 and then reflect it in this quantity per mil. And this is just a really convenient way to basically describe very small changes in isotope abundance very consistently. But you'll see this delta 18O a lot, so this is sort of what's underneath the hood. So one thing to keep in mind here is that the delta 18O is greater than 0 when you're enriched in the heavy isotope relative to the standard. So anything that is a positive value in delta 18O has more oxygen 18 than you would expect. So there's lots of processes in nature that influence the relative abundance of oxygen 18 and oxygen 16. They tend to be very small and only important in certain scenarios. But one process that has a global impact is evaporation. And so you can think about these delta 16O and delta 18O having kind of the same total energy, but because delta 18O is more massive, it has more neutrons, it weighs more, it's kind of moving around a bit slower. If you think back to the equation for kinetic energy, 1/2 mv squared, for things that have the same energy, when you have more mass, you have less velocity. So anyway, you can imagine this 16O is kind of jittery, it's bouncing around everywhere, it's moving a bit. And this delta 18O is a lot more sluggish. So this extra 2 mass units really kind of slows things down. And that sort of affects molecules that have oxygen in them, like water, that affects the speed that those molecules move and affects their chemical reactions. So for instance, water with a 16O will actually boil at a slightly lower temperature than a water with oxygen 18. And that's because these water molecules, they're moving around a bit faster and they're just bursting to get out of this liquid water and turn into a gas. Versus the oxygen 18, because it's moving a bit slower, it's not ready to make that jump quite yet. And this is true for boiling water. This is also true for evaporation. So if you just have a glass of water on your desk, you come back over time, it'll lose volume because you have evaporation of water into the atmosphere. In the ocean, this happens, and this is how clouds are made. And what happens is that cloud water is actually enriched in 16O. It's depleted in 18 oxygen. So it has a negative delta 18O. So now we can imagine 2 different environments or 2 different climates. The first one, let's say you have a warmer climate, higher temperatures, and so you still have an ocean here. You have evaporation from the ocean, and this is preferentially incorporating the light oxygen, right? Then that falls on the continent as rain, and then that runs off back to the ocean. So you have this rain that's depleted in heavy oxygen, so it's light. That rain comes back to the ocean. So there's no change in the ocean oxygen isotope content because you have this closed cycle, right? Water goes up, it rains, it comes back. But now think about this cold climate, right? Remember those ice sheets that were covering all of North America, huge parts of Europe, etc. Now you have the same evaporation process, and so you're enriching these clouds in the light isotope, 16 oxygen. These come down as snow on land, but now they stay here. They don't run off the continent. They stay there for thousands and thousands of years. And so over time, you tend to form ice sheets that are really light isotopically. And then you have the ocean, as it loses sea level, become isotopically heavier. So the delta 18O of seawater will increase when you have bigger ice sheets because you're locking away all the 16 oxygen on land. So even though we expect that the ocean water becomes isotopically heavier in the past, we still have a problem. And that's that there's no ancient seawater still around. the ocean is constantly mixing, and the water in the ocean today is basically the same water that was in the ocean in the past. And now that the ice sheets are melted, all that 16O that was locked away is returned to the ocean. So we can't really measure delta 18 oxygen from 20,000 years ago. But fortunately, water isn't the only molecule that has oxygen atoms in it. So look, for example, at the formula of calcium carbonate. You have calcium, carbon, you have 3 oxygens here. So this mineral is actually almost half oxygen by weight. And this is abundant in marine sediments. It's preserved throughout the tropics and the equator, so there's these vast reservoirs that we can go and tap into and make reconstructions of the past. And we can do this for over the past 100 million years. Over longer time scales, you start having issues because the seafloor doesn't always get that old. And so you could have subduction of those carbonate sediments and you can't really access those anymore, or they turn into metamorphic rock and becomes a bit more complicated. But what we can do is we can go into the sediments, so we can look for certain organisms that make calcium carbonate rich shells, like these foraminifera here, call them forams because we don't have time. And we can basically measure the oxygen and isotopic composition of their skeletons, and then we can use that to infer what the seawater was in the past. All right, and so the sort of quest to go out and find sediments to sort of do these reconstructions consumed a lot of people. This is a huge field of oceanography, is basically studying ocean environments in the past using sediment records. So if you're doing this, what you do is you go out on these big ships, these drilling ships. You see here, this kind of looks like an oil rig here. This is this derrick tower. This allows you to drill sort of straight down, basically to the bottom, to the seafloor, and then into the sediment column, which can be kilometers deep in some places. And the goal here is to recover sequences of sediment that are continuous. They go back in time. So at the top, there's sediments from this past year, basically, or now. And then you go back through and you get sediments that are thousands of years old. Depending on where you are, they might even be millions of years old. But anyway, those are brought up to deck and they're processed here. You can see this is like a 10 meter or so stretch of sediment from someplace that's looks pretty muddy, so probably closer to the coast. And you have all this whole line of scientists who are going to be cutting it into sort of 6-foot chunks just to make it more manageable. They're going to be cutting it in half and sort of archiving half of it and then working with the other half to divvy it up into different samples and chemical analyses. And they're going to do things like barcode it, tag it, so that other researchers who aren't able to fit on this boat can still study how different proxies for past change using these sediment cores. So this is what a core that's really rich in calcium carbonate looks like. So you can see here, these are sort of 6-foot sequences of the core. Let's say this is the most recent, the most modern sediments, and then as you go down, they get older, and then this is the next sequence. This is older still, older still, older still. You can see here this kind of brown sequence, which I think is a volcanic ash layer. So you can imagine this is an easy way to sort of establish chronologies or timelines, is that if there's a global eruption, then that will leave an ash layer, and that you might find that in different cores from different places. So you can kind of align sediments from one region of the ocean to sediments from another region of the ocean. Just make sure that they're at the right time. Anyway, if you took a bunch of these sediments and you looked under a microscope, what you'd find are these forams. So these are right over my head. You can see these shells here, these ones too. So these are what you'd want to pick out. What you can do is you can basically identify the species of foram based on the morphology, the structure of these shells. And so what scientists do is they'll go in, they'll have these really tiny tweezers, and they'll go and pluck them up from the microscope and collect them, and then actually analyze those for their oxygen isotope content. So after thousands and thousands of measurements, this is the sort of curve of delta 18O oxygen that we now have from a whole bunch of deep sea sediment archives or cores that are averaged together. This just sort of show the global signal amidst any kind of regional variability in where the actual core was taken from. So on the y-axis here, you can see the axis is delta 18O. And in modern sediments, these values are pretty low. It's around minus 0.8 per mil. So they have a lot more 16 oxygen than 18 oxygen, even compared to something, a baseline standard like seawater. And then when you go back in time, you see this huge shift. And so instead of being minus 0.8, now you're close to plus 0.6 per mil. And that stays sort of in this positive territory for over 50,000 years before coming back down. This is the last interglacial period, the last warm period. And then same thing happens. You have a swing towards more positive delta 18O. It stays that way, swings down, and then back and forth and back and forth. And in the next video, we'll sort of talk about this time scale because it's fascinating, but it's a bit complicated. But what we can do now is we can look at our new knowledge of how this delta 18O system works and make some inferences about climate. So we know that when there's lower values of delta 18O, that corresponds to warm conditions where there's small ice sheets. Right? And so the small ice sheets are not retaining light isotopes. And so as a result, this delta 18O value is low. But then during things like glacial periods, this delta 18O is higher. And we know that corresponds to more storage of 16O on land. As a result, the ocean, what gets left behind, becomes heavier. And so you can see that these are pretty consistent changes in ice sheets that happen repeatedly over time. These are the glacial cycles. So to be fully accurate, it's important to acknowledge another influence on the delta 18O of calcium carbonate. So this is really a mixture of two signals. We talked about seawater delta 18O and the role of the role of ice on continents in setting this global value of delta 18O. But there's also an important influence of just seawater temperature straight up. At warm temperatures, the delta 18O of calcium carbonate is the same as the delta 18O of seawater. There's sort of this forward and reverse reaction between water and carbonate ion. So you can see here on one side of the equation you have the 18O in the oxygen. On the other side, you have it associated with one of the three oxygens in the carbonate ion. Anyway, these reactions go forward and back, and they interchange. So there's no difference in where this oxygen 18 sits. Half of it will be, proportionally in water, half of it will be in carbonate. And so when organisms like forams, when they make their calcium carbonate skeletons, they'll basically be drawing from this carbonate pool and incorporating, the same abundance of 18 oxygen as there is in water. So that's how that works. But when you have colder temperatures, this chemical reaction, the balance changes, and actually you have more 18 oxygen associated with carbonate than you do with water. And so this is oftentimes called a paleothermometer, basically because this is a temperature-dependent reaction that is recorded in some kind of mineral phase that you can then measure later on. So at low temperatures, you have more heavy oxygen in carbonate than in water. And so if you have a good calibrated system, you can use this as a paleothermometer, like I just said. So here on this y-axis now is the difference in delta 18O from the calcium carbonate versus the water that these forams are grown in. You can actually do this in the lab to make sure that these relationships are well defined, not influenced by changes in salinity or other sort of compounding variables. But here you can see that this essential line that emerges, and so when you have warm temperatures, you have very little offset, and then when you have colder temperatures, you have increasingly positive delta 18O in your carbonate versus what's in your seawater. So this is fractionating under cold environments. So to recap, during glacial periods, we now see that the delta 18O of calcium carbonate becomes heavier. And this is because, first, there's more storage of light 18O on ice sheets. So the starting seawater delta 18O is heavier. And then there's this second effect that adds to this. So when you have cold climates, colder ocean temperatures, the calcium carbonate will have a greater preference for 18O. And so that will be stored in calcium carbonate. So the delta 18O of calcium carbonate becomes heavier because the seawater is changing, and this balance between seawater oxygen and mineral oxygen is shifting in the favor of the mineral. And so you can use this delta 18O proxy as a proxy for combined global temperatures and ice sheets volumes. And this is because when ice sheets expand, the climate cools. And so these two forces are moving in the same direction. So we can use this as an integrated sense of climate. But that said, if there's a way to reconstruct ice sheet volume from some other way, and often this is done by looking at sea level records. So you can go to these sort of fossilized coral reefs and date them, and then figure out, well, if they're at 300 feet below the ocean now, they're not growing there, they're fossilized. The sea level must have been down that way, down that much, so that those corals would have had enough sunlight to grow. So those types of reconstructions, we can develop an independent record of sea level. And then we can calculate temperature directly from delta 18O. So we're basically using delta 18O, subtracting the sea level component, and then that leaves the temperature paleothermometer by itself. So in the next few videos, we'll sort of explore how this actually works out in climate records. But now you have a sense of where these numbers are coming from, the type of work that's involved to get there, and how they're sensitive to both ocean volume and ocean temperature, but how both of those influences kind of work in the same direction to describe these cold periods in Earth's climate where there's glacial times, and these warm periods where there are, conditions like today where there's smaller ice sheets